15 asks, what type of reaction is this? This is maybe the trickiest one, and I overheard some of you talking in the auditorium when we did this one. Why couldn't this be double replacement? Because it looks like two compounds. Why couldn't they switch partners? Well, if you think about it, it'd be calcium and sulfur switching partners. And in this case, they both have the same partner already. So they couldn't really exchange partners and both be dancing with oxygen all over again. That doesn't work. So it can't be double replacement. It can't be combustion because we don't have a fuel or oxygen, so that's out. And it isn't going to be decomposition because, again, decomposition tends to be when one thing is going to break down into two or more things. All that's left is synthesis. And in fact, if we think it through, we can come up with the products by name and by formula. The name of my product would be calcium sulfate, CaSO4, in the synthesis reaction. Number 16, we've got CH4 and oxygen combining to make what? Well, this is a combustion reaction. That's the simplest, lightest fuel we can think of, basically. Methane, about the simplest fuel gas that there is. And carbon and hydrogen and oxygen coming out the other side will give me, well, it really could be any of these choices, I suppose, if I didn't know anything else about combustion. But knowing that combustion always produces water as a gas, that leaves me A and D as my choices. And knowing that combustion always produces either carbon dioxide or carbon monoxide, the only good choice I've got here is letter D. Carbon dioxide and water being produced. So that's letter D. 17. What type of reaction is this? Well, this is one compound breaking down into potentially two or more things. If we're given one compound on the left side, there's really only one kind of reaction it can be, and that's decomposition. It doesn't ask you here what those products are, what kind of reaction it is simply, and that's letter B. Just for the record, you'd be making water and carbon dioxide when this comes apart, as was mentioned earlier on. 18, we're taking hydrochloric acid and putting it together with potassium hydroxide. Now, not only is this a double replacement reaction, hydrogen, chloride, potassium hydroxide, essentially, switching partners, it's a specific kind. It's that neutralization kind of double replacement reaction, where when the two partners switch in a neutralization reaction this way, we end up making water. Hydrogen goes with hydroxide, HOH, and that's water. So we're going to make water as our product. And right off the bat, I can find that only letter B gives me that. The only other product that I could make then would be if the potassium and the chloride got together. That gives me potassium chloride. So KCl and water, that's letter B in a double replacement reaction. 19. Which of the following is least likely to decompose and produce a gas? Well, all of these could decompose. The question is, which will not produce a gas, we expect? Well, look through here. I've got calcium, carbon, and oxygen. When that decomposes, if I think about it, it's going to make carbon dioxide, which is a gas. And HNO3, that's an acid. When acids decompose, they tend to make water and a non-metal oxide. Basically, almost all non-metal oxides at room temperature will be a gas because non-metals with non-metals tend to like to make gases. In this case, we'd get nitrogen and oxygen together at the end in dinitrogen pentoxide, which is a gas. Even if you didn't know that, though, let's look ahead to the next one. Potassium and chlorine, those are two elements that together make a salt, but when I pull them apart, I would get potassium and chlorine, a gas. Chlorine's a gas. And again, even if you didn't necessarily remember that, hopefully you'd look at letter D and say, here I've got iron and sulfur. And somehow iron and sulfur just can't be gases, typically, when these things come apart. Iron's a metal, sulfur's a non-metal that happens to be a solid at room temperature. Now, could it come out as gaseous sulfur? Probably not, because sulfur tends to combine with oxygen really fast, and you wouldn't get sulfur by itself. When we take iron sulfide apart, we're likely to get iron and sulfur maybe as liquid sulfur at the best. So we're not going to get a gas from letter D. Neither one of those is going to come out as a gas. Number 20, we've got magnesium nitrite decomposing. How does this work? Again, this is a ternary salt, so we're going to get a metal oxide and a non-metal oxide. Well, that leaves me B, C, and D as my choices. Those are the only three choices now that have a metal oxide, magnesium oxide, and a non-metal oxide with nitrogen and oxygen together. So A is out. What about B? Well, if I look at B, magnesium and oxygen going together wouldn't make MgO2 if we call it magnesium oxide. So magnesium oxide is MgO, not MgO2. So B is out. That leaves me with C and D. And this is where I have to think about what is nitrogen's charge in the original compound, and what will it be then, that same number at the end? Well, if I go through here and think about MgNO2, 2, I've got one magnesium. That's contributing a +2 to my oxidation number total. I've got 4 oxygens that are each contributing a -2 to my oxidation number total. 4 oxygens times -2 makes -8. The magnesium contributes +2. So I have -8 and +2 so far. That means overall, the magnesium and the oxygens put together give me a -6. The 2 nitrogens that are in this compound have to give me a +6 in order to balance this thing out. 2 nitrogens that give me a +6 total means each nitrogen is worth a +3. So magnesium's +2, nitrogen's +3, and oxygen, as always, is -2. Well, if nitrogen's +3, and I bring it across to the other side and put it together with oxygen at -2, a +3 and a -2 will combine in a 2-to-3 ratio, and that's what we see in choice letter C, MgO plus N2O3. Now, this is a complicated idea with oxidation numbers for some folks, and this is frankly what hangs people up on decomposition and synthesis reactions. If you're still struggling with these oxidation numbers, please come and see Mr. Mitchell or myself ASAP for some help in order to get this problem solved. It's not hard to get you figuring it out if you sit down with us for 10 minutes, and we'll have you straight on the way to success with these decomposition reactions. 21, the likely second product here will be most likely a precipitate, a gas, water, or a soluble salt. Well, what's the other product going to be? I've already taken the magnesium and the nitrate and put those together to make that product. What's the other product going to be? Well, it's going to be HBr, hydrogen with bromine. Hydrogen with bromine are those 2 nonmetals that are bonded through a covalent bond or maybe a polar covalent bond. When we have 2 nonmetals bonded together, well, that's not water. We don't have water here. And we don't have a salt. Remember, a salt will be a cation with an anion. Hydrogen bromide is really not a cation with an anion. It's 2 nonmetals that have found a way to bond together, covalently or polar covalently. And in this case, hydrogen bromide comes out as a gas. Hydrogen bromide gas when 2 nonmetals. All right, so on number 22, we have potassium iodate. Now, potassium iodate is an iodate, obviously, along with the chlorates and the bromates. The iodates do things just a little differently than the other ternary salts we've talked about. Typically, we'd expect them to break down like a ternary salt, but an iodate, a chlorate, and a bromate will all break down a little differently. Again, what happens is oxygen just sort of comes out by itself. So the oxygen escapes as a gas, and that leaves behind the metal, which is potassium in this case, and the halogen, which is iodine in this case. Chlorates, bromates, and iodates all contain chlorine, bromine, or iodine, respectively, and that element, along with the metal, stays behind. The oxygen leaves. So as oxygen comes out of KiO3, or potassium iodate, the oxygen escapes, and the potassium and iodide are left behind. In this example, in the questions below, or the options below, the only ones that have potassium iodide and oxygen would be C and D. So what's the difference between those? Well, in D, the oxygen is shown as diatomic, and that's correct. Oxygen is one of those 7 elements that comes out diatomic, and so D is our choice. Number 23, which of the compounds below will not decompose to form a diatomic element? Well, water would decompose to form hydrogen and oxygen. Both of those are diatomic. Potassium chlorate would be one of those elements. Again, a chlorate, a bromate, or an iodate that gives off oxygen gas, and that would be a diatomic element. Letter D, we have sodium nitride, and when that decomposes, we would have sodium and nitrogen. Nitrogen's a diatomic element. Now, if you look at letter C, you might think, well, that's got hydrogen and oxygen in it. Both of those are diatomic elements. But remember, this is an acid. When sulfurous acid, as you see in C, decomposes, it'll produce not hydrogen and oxygen and sulfur, but water and sulfur dioxide. Water and a nonmetal oxide. And neither of those is a diatomic element. So the one that doesn't form a diatomic element on this list is C. Number 24, we have diphosphorus pentoxide and water combining. This is a nonmetal oxide and water, which are going to make together an acid. If you look at the choices down below, only A and D really look like acids at all. Hopefully you spot a problem with D right away, in that phosphite, the ion PO3, has a negative 3 charge. That would mean we'd need to have 3 hydrogens to go with it because hydrogens charge of +1. 3 of those would balance out the phosphite's negative 3 charge. So letter D isn't quite even an appropriate acid formula. Letter A shows phosphoric acid, H3PO4, hydrogen and the phosphate ion, which is negative 3. What you want to make sure and double check in a question like this is what is phosphorus's charge at the beginning of the compound, or the beginning of the equation, and that phosphorus in the P2O5 would have a +5 oxidation number. The oxygen would have a -2 oxidation number. So again, looking at that, +5 and -2 would give us a total of +10 and -10 for the oxidation numbers in that compound, or overall charges on the oxidation numbers, and that would give us a neutral P2O5. So that phosphorus with a +5 oxidation number, that carries through into the H3PO4, into the phosphoric acid, letter A here, where the phosphorus also has a +5 charge. So that's our answer, letter A. And the final question, which of the following situations is most likely to result in incomplete combustion? Incomplete combustion, remember, means that combustion is happening in an environment where there is a shortage of oxygen. The oxygen's running out for some reason. Well, if we're letting a Bunsen burn in the lab, there's plenty of oxygen all around, otherwise we would all feel lightheaded. When you're burning a log in a bonfire, you're outside. In the summertime, there's plenty of oxygen all around you. If you're burning a candle in a birthday cake, for example, on letter D, there's hopefully, again, people all around for the birthday, and they're all hopefully not feeling dizzy, so the oxygen mustn't be in short supply. But if I was to burn a candle in a tall, deep jar, at the bottom of that jar, it's quite easy for the oxygen to run out because the carbon dioxide is being made by the burning candle flame, and carbon dioxide could accumulate down there and, to some extent anyway, reduce the oxygen that's flowing in. The one thing candles like that have going for them is that the heat is rising and creates somewhat of a current. But if you're in a tall, deep jar, it's hard for air to move all the way down to the bottom of that candle jar and reach the flame. So after a while, you'll find those candles that are far, far down in deep jars tend to not burn very well or go out far too early for our liking. That's why when candles burn down a big cavity in the middle of a candle, it's hard for them to burn very well. Part of the reason why, anyway. So there's your 25 answers. If you have questions about these in any further detail, please see one of your teachers about them, and we'll be glad to go over them in more detail with you.